Theorem: let M be a closed linear subspace of a Hilbert space H. Let X not belong to M, but X belongs to H. Let D be the distance of X to M. Then there exists a unique Y0 belongs to M such that norms of X minus Y0 equals to D. Proof: let M be a closed linear subspace of H. X not belong to M and D be the distance from X to M. Then D equals to infimum of norms X minus Y such that Y belongs to M. Then there exists a sequence Yn in M such that norms of X minus Yn tends to D. Let Ym and Yn be the two vectors of a sequence Yn. Since M is a linear subspace of H, therefore Ym and Yn belongs to M, which implies Ym plus Yn upon 2 belongs to M. By the definition of the D equal less than equal to norms of X minus Yn plus Ym upon 2, or 2D is less than equal to norms of 2x minus Yn plus Ym, or norms of 2x minus Yn plus Ym is greater than equal to 2D. Equation 1, or norms of X minus Yn plus X minus Ym greater than equal to 2D. Applying the parallelogram law for the vectors X minus Yn and X minus Ym, norms of X minus Yn plus X minus Ym norms whole square plus norms of X minus Yn minus X minus Ym whole square equals to 2 norms of X minus Yn square plus X minus norms X minus Ym square equals to 2 into D square plus D square as M and N tends to infinity, or norms of 2x minus Yn minus Ym whole square equals to norms of Yn minus Ym whole square equals to 4D square, or norms of Yn minus Ym whole square equals to 4D square minus norms of 2x minus Ym whole square, which is less than equal to 4D square minus 4D square equals to 0 by equation 1, or norms of Yn minus Ym is whole square is less than 0, but norms of Yn minus Ym whole square is greater than 0 as Mn tend to infinity. Therefore sequence Yn is a Cauchy sequence in M. Since H is complete and M is closed subspace of H, therefore M is complete. Hence Cauchy sequence Yn is in M is also convergent sequence in M. Therefore there exists a vector Y0 in M such that Yn tends to Y0. Now norms of X minus Y0 equals to norms of X minus limit Yn equals to norms limit X minus Yn equals to limit norms of X minus Yn equals to D. Hence Yn is a vector in M such that norms of X minus Y0 equals to D. Uniqueness of Y0: if possible, let there exist Y0 and Y1 belongs to M such that norms of X minus Y1 equals to D and norms of X minus Y0 equals to D. We shall show that Y0 equals to Y1 since M is a subspace of H, so y0 and y1 belongs to M, which implies y0 plus y1 upon 2 belongs to M. Therefore, by the definition of the D, we have norms of x minus y0 plus y1 upon 2 is greater than equal to D, which implies norms of 2x plus y0 plus y1 is greater than equal to 2D. Equation 2. By the parallelogram law, norms of x minus y0 plus x minus y1, norms x minus y0 plus x minus y1 whole square plus norms of x minus y0 minus x minus y1 whole square equals to 2 into norms x minus y0 whole square plus 2x norms of x minus y1 whole square equals to 2 into d square plus d square, because norms of x minus y1 equals to d and norms of x minus y0 equals to d, which implies 4d square, or norms of 2x minus y0 plus y1 whole square plus norms of y1 minus y0 whole square equals to 4d square, or norms of y1 minus y0 whole square equals to 4d square minus norms of 2x minus y0 plus y1 whole square, which is less than equal to 4d square minus 4d square equals to 0 by 2, or norms of y1 minus y2 whole square is less than equal to 0, but norms of y1 minus y0 whole square is greater than equal to 0. Hence, norms of y1 minus y0 equals to 0, which implies y1 minus y0 equals to 0, which implies y1 equals to y0. Hence, proof.